So what is the best way to drive 7-segment displays on a breadboard? We have all seen messy setups like this one here. In fact, that is my own circuit from around a year ago. But in today's video, I will show you step by step how to use the TLC5916 driver IC and what you can do to arrive at a super clean breadboard layout that works for as many 7-segment displays as you like. And if you stick around till the end, I will show you how I used to do it before, what was wrong about that, and what is better about the method I'll explain today. So here is the final product of this tutorial. This PIC microcontroller on the left here sends out numbers to the 4 displays. And the numbers are somewhat meaningless, even though they do spell out 5916 sometimes. But in a real-world application, these numbers could be the time or any other numerical information you want to display. Under each display, there is a TLC5916 driver IC, and we plug in the displays right on top of them, which I think gets you a really clean breadboard setup, even though it means that you have to solder just a little bit. But if you don't want to solder, you can of course still use the TLC5916 driver IC and connect them to the displays with DuPont-style wires. And there is one more thing. I included a potentiometer that allows you to adjust the brightness of the displays.
Hi, my name is Jens and I believe that everybody can learn electronics. We have a lot of ground to cover today, but I promise you it's gonna be worth it.
First off, if you want to follow along with this tutorial, you will need a 400-pin breadboard, a 4.5-volt AAA battery compartment, and of course also the batteries, the PIC16F1455 microcontroller, the TLC5916 driver IC, a common anode 7-segment display, a 1K resistor, a 4.7K potentiometer, 2 100 nanofarad capacitors, and one 100 microfarad capacitor. If you want to add more digits, then you need to add more of these components, one for each digit. And of course, you will also need more breadboards. You also need the PIC kit 3 with a 6-terminal connecting cable, as well as single-stranded wire. There is a link in the description to the companion article on friendlywire.com, and if you click on it, there is the usual components box on the right side, where I have a detailed list for you with links to all the components I just showed you.
Now before we jump into the TLC5916 real quick, what is a 7-segment display and how do we drive LEDs?
A 7-segment display is just a collection of 7 LEDs that are arranged in this figure 8 form, and the segments are named like this. If you turn on some of them, you can display the numbers 0 through 9 and many text characters as well. Usually either all the positive or all the negative terminals of the LEDs are connected together, and we call those configurations common anode or common cathode. And in this tutorial, we will use the common anode version. Now, each LED comes with 2 basic numbers, the forward current and the forward voltage, and you can find those numbers in your LED or 7-segment display datasheet. The forward voltage depends only on the color of the LED, and the forward current can vary, but for many LEDs it is around 20 milliamps. The higher the current, the brighter the LED, but if the current is too high, the LED is destroyed, so make sure to check what your LED's forward current is and don't exceed it.
So there are 2 ways to drive LEDs, and here's the first one.
Say you run your circuit at 4.5 volts like we do in our tutorial right now, and you want to drive a green LED at 20 milliamps. Its forward voltage is around 2.2 volts. You can connect it to 4.5 volts and insert a current limiting resistor like this, and it doesn't matter if the resistor is before or behind the LED. The LED itself needs 2.2 volts, so the rest of the 4.5 volts needs to drop over the resistor, and you can calculate it like this. The closest value that you can buy in store is 120 ohms, which means that the LED current is around 18 milliamps, which is great. If you have multiple LEDs in series, the forward voltages add up. So if you have 2 green LEDs, the combined forward voltage would be around 4.4 volts, and you would need only a very small 5 ohms resistor to arrive at the required 20 milliamps. Also, this means that your supply voltage has to be at least equal to the sum of the forward voltages. It's better if it is slightly larger. There are some problems with this kind of approach. The forward voltages can vary a little bit due to imperfections in the LED's manufacturing process, even for the same type of LED, and that leads to different brightnesses, especially if you have many LEDs in series. Also, if your supply voltage changes from 4.5 volts to something else, you need to recalculate all resistors. That's why there is a second and I think better way to drive LEDs, using a constant current source. This source is usually built in between the LED's cathode and ground, so it makes sense to use common anode 7-segment displays in this case. And then if you set the constant current source at 20 milliamps, you don't have to worry at all about calculating the current limiting resistor, and it works for a wide range of supply voltages, so not just 4.5 volts, but also 5 volts, 6 volts, and so on.
Maybe you already guessed it, the TLC5916 already comes with such a constant current source. And now we just have to learn how to use it with a microcontroller.
Here's our simple schematic for one digit only at this point. We'll add more later. The PIC16F1455 microcontroller sends the data to the TLC5916 driver IC, which controls the LEDs inside the 7-segment display. This symbol down here is just the power connection for the TLC5916, and we will later use this connector up here to program the microcontroller. This potentiometer adjusts the brightness of the display, more on that later. But see this resistor R2 here? It tells the TLC5916 at what current the LED should be driven. If you have a current in mind, you can calculate the resistor value like this. Looking into the datasheet of our 7-segment display, we see that the forward voltage is 4.4 volts to 5 volts because it uses two LEDs in series for each segment. This means we are running it a bit tight here with our 4.5 volt supply voltage, and it would be better to use 5 volt in a permanent project. The forward current of this display is 20 milliamps. So in our case, because R2 is equal to 1 kilo ohm, the forward current is set to 18.75 milliamps, which is below the maximum of 20 milliamps that our LEDs can handle. But keep in mind that the difference between the supply voltage and the LED forward voltage is converted into heat inside the TLC5916. So it's good if your supply voltage is only slightly higher than the forward voltages of the 7-segment display. Otherwise, the TLC5916 might overheat and shut down. Okay, so here comes something really important. We are switching a bunch of LEDs on and off, so the total current flowing into our circuit can change quite rapidly. To balance this out, we have to add C3, a large 100 microfarad capacitor, and this is also called bulk capacitance. It is also a good idea to add smaller 100 nanofarad bypass capacitors, here they're called C1 and C2, in close proximity to all the chips, meaning to the PIC microcontroller and all TLC5916 drivers. Go and check out Dave Jones's video on this if you want to learn more.
Now, how do we get data inside the TLC5916 to make it display a symbol?
The TLC5916 is a shift register, and you can learn all about those in my scrolling text video right here. In a nutshell, a shift register is very much like a conveyor belt for 8 bits. The bits go in on one side, and whenever the clock pin is pulsed, they move one to the left, and eventually fall out on the other side. The idea here is very simple. Each one of these 8 bits is connected to one segment of the display, so by sending in a sequence of ones and zeros, we can create any pattern we want on the display. For the TLC5916, the data input is called serial data in, or SDI. The clock input is abbreviated CLK, and a pulse on the latch enable, or LE pin, makes sure that the outputs Q1 through Q8 are updated to whatever bits are on the conveyor belt in that moment. And last, /OE is the output enable pin. It is active low or inverted, which is why it is called /OE and not just OE. When it is 0, the outputs are enabled and reflect the current status of the 8 bits, but when it is 1, all outputs are turned off.
Let's have a look at a typical timing diagram for transmitting 8 bits to the TLC5916.
Here you can see the 4 control inputs and the 8 outputs. Let's talk about the logic signals we need to apply to them to transmit a binary number, say 11010100. /OE can be kept low the whole time. Then before each clock pulse, the correct data bit has to be set. We have to start with the highest bit and finish with the lowest bit. The arrows on the clock pulses mean that the logic level at the SDI pin is red at every rising edge of clock. After transmitting the data, we just need to pulse the latch enable pin once, and then the new data appears on the outputs like this.
Now I hope all of this isn't too confusing, but if it is, then don't worry about it. It's completely normal. It's actually part of the process. In that case, you might want to check out my video on the scrolling text display that you can see behind me right there, because in that video we describe the details of shift registers in a lot more depth than in this video right now. But in the next step in this video right here, I actually want to add even more digits to our schematic. Let's do it.
The 7-segment displays are connected to their TLC5916 drivers just like before, and the clock, latch enable, and output enable pins are all connected in parallel. The data output of the TLC5916 is called serial data out, or SDO for short, and we can connect that data output of the first register to the input of the next one, so that the data is passed along as soon as it leaves the first register, and we can just keep doing this forever. This is called cascading, and it is super useful.
Alright, so now I want to talk about the more advanced TLC5916 stuff, which is related to dimming. If you don't really care about those technical details, then you can just jump to this timestamp right here and jump straight into the build. But for all of you that want to learn more about dimming, let's have a look at the potentiometer R1.
It is connected to the PIC16F1455's 8-bit analog to digital converter that translates the potentiometer's position into a number between 0 and 255. You can learn more about ADCs in this dedicated video right here. One simple way to dim the LED display is to use the pulse width modulation module of the PIC16F1455 and connect it directly to the /OE pin. This turns the LEDs on and off very rapidly, typically a few thousand times per second, and creates the illusion of a higher or lower brightness depending on how long the LEDs are on and off. Because the human eye is slow, it perceives a sort of average brightness if the LEDs flash fast enough, which is why PWM works very well for humans. But it doesn't always work well for digital cameras, which are much faster. I have a separate video on PWM right here if you are interested. But the TLC5916 has a separate feature that we can use to dim the LEDs, the so-called special mode. This is in contrast to the normal mode, where it works as a shift register that we just talked about before. You can get into the special mode by applying a special sequence of pulses on the clock, output enable, and latch enable pins like this.
And then you can actually send the command bits. Now with those you can adjust the current from 25% to 100%. You can't dim all the way down to 0% with this, which you could with PWM, but on the plus side, this dimming method doesn't involve any flickering. So if you have a super fast camera, this will work just fine, which is why I really like this method.
So what we do is take the ADC value of the potentiometer and translate it into the correct command bits. There are 128 different current levels, so we can divide the ADC value by 2 and then use that number and convert it into the correct command bits. Remember that if we have more than one display connected, we have to send the command bits that many times as well, so that it arrives at the last display in the row as well. And here is how we send the command bits. B0 through B5 encode a number between 0 and 63, and HC is 0 for the range of 25 to 50% of the current, and HC is equal to 1 for the range of 50 to 100% of the current. And after sending those command bits, we have to leave the special mode again to go back to the normal mode by applying some more arcane pulses on the clock, output enable, and latch enable pins like this. Okay, it's not a secret, it's actually explained really well in the TLC5916 datasheet that you can also download on my website as well. And that's it.
Alright, let's go and build the circuit. First we have to take a look at the LEDs.
The TLC5916 pinout is like this, with 4 outputs on either side. Let's rotate it by 90 degrees and place a 7-segment display next to it. Now there are of course many different types of 7-segment displays, but the ones I like most for this purpose have pinouts like this. Capital A is the common anode, but all the other 8 pins are the segments, and you can see there are also 4 on either side. So let's take a fresh 7-segment display. First, let's bend the common anode pin out by 90 degrees on the top side. Then we can bend the other anode pin at the bottom out of the way inwards because it's electrically connected to the other anode pin we just dealt with and we don't really need it. Now we can carefully bend the remaining segment wires like this so that they are on the same perfect 0.1 inch grid and are exactly at the right location for the 4 pins of the TLC5916. Now we have to extend the pins by soldering simple American wire gauge 24 or 0.6mm wire to them, because after bending they are too short. Our 7-segment display is actually too big in this direction here, so we also need to bend the pins inwards like this. This process works for smaller 7-segment displays as well, and I think it's an amazing space saver because now the displays plug in right on top of the TLC5916 driver ICs. But if you don't want to solder, you can of course also use DuPont style wires like this.
But before we get ahead of ourselves, let's go back to the empty breadboard and build the circuit together step by step. Now I'll be doing this for 4 digits, but you could of course do this for 1 digit or 2 digits or 500. I mean, that's really your call.
Place two 400-pin breadboards in front of you with their row 1 facing to the left. Insert the PIC16F1455 in row 8 and the 4 TLC5916 driver ICs in rows 19, 2, 12, and 22. Make sure their notches point to the left. These are the notches and not those weird confusing circles. Connect the power rails between the two breadboards. For the upper rail we need to connect both VDD and ground, and for the lower rail it is actually enough to just connect ground. Next, connect the power pins to the integrated circuits. The PIC16F1455 has VDD at pin 1 and ground at pin 14. The TLC5916 ICs have it exactly opposite. Their VDD pin is at pin 16 and their ground pin is at pin 1. For this reason, I always recommend to use colored wires to avoid any sort of confusion. Then connect both power rails on both sides of the left breadboard. Insert the 100 microfarad bulk capacitor C6 into the power rail. Make sure its negative terminal is connected to the negative power rail, which is blue, and its positive terminal is connected to the positive power rail, which is red. Electrolytic capacitors such as C6 have a big minus sign on their negative terminal, so it is easy to spot. Then insert the 100 nanofarad bypass capacitors C1 through C5 between the VDD and ground pins of all the ICs. These capacitors can be plugged in either way, but try to place them as close to their chip as possible. Now let's work on the ICSP programming connector, which will be plugged into rows 1 through 6 later. Start with the master clear cable from row 1 to pin 4, the VDD wire from row 2 to pin 1, and the ground wire from pin 3 to pin 14. The programming data wire in row 4 goes to pin 10, and last the programming clock wire in row 5 goes into pin 9. Next, place the 1 kilo ohm current adjusting resistors R2 through R5 between pins 15 of each TLC5916 driver IC and ground. Now connect the data lines. The first connection is from pin 7 of the PIC16F1455 to pin 2 of the TLC5916. All other connections are from the SDO output, pin 14, to the SDI input of the next driver at pin 2. Let's move on to the output enable connection. These are all in parallel and start at pin 5 of the PIC16F1455 and connect to pin 13 of each TLC5916 driver IC. These wires look a bit messy, but that is because I connected them to the same breadboard connection hole to save some space. The clock lines are also connected in parallel. Connect pin 6 of the PIC16F1455 to pin 3 of all the TLC5916 driver ICs. Last, the latch enable lines connect pin 8 of the PIC16F1455 to pin 4 of all the driver ICs. Now it's time for the magical moment, plugging in the 7-segment displays. If you have followed the instructions from before, then this installation process will be super smooth. Make sure to connect them correctly though, so that their pins line up with the pins 5 to 8 at the bottom and with pins 9 to 12 on top of the drivers. Their anodes plug into the power rail automatically. Finally, plug in the potentiometer R1. The red and black wires are the outside terminals of the potentiometer, and the green wire is the center terminal. And now connect the 4.5 volt power cables. I recommend to plug them into the top right as close to the LED power rail as possible. But of course nothing happens yet because we first have to flash the PIC with the PIC Kit 3. Connect the 6-terminal cable to rows 1 through 6 and make sure the yellow cable is connected to row 1 on the breadboard side and to the triangle symbol on the PIC Kit 3. I won't go through the details of the source code in this video because I think it would take way too long, but you can go check out the companion article after watching this video where I explain the source code in great detail and line by line. Now plug the PIC Kit 3 into your computer and start the MPLAB 10 IPE. Select PIC16F1455 under Device and the PIC Kit 3 under Tool. In the power settings, make sure to select the high voltage programming mode. Click back on Operate and then on Connect. Confirm this dialog and then the PIC16F1455 should show up down here. Then click on Browse and open the hex file and finally click on Program. The PIC-Kit3 starts blinking and after a few seconds the hex file has been transferred and the circuit is now functional. Now unplug the PIC-Kit3 and we're done. With the 4.5 volt battery supply, the large 7-segment display can be a bit dim, so I switched over to my bench power supply which provides 5 volt instead, and that looks much better. And if we turn the potentiometer, we can actually adjust the brightness of the LEDs. They don't turn off completely though, because the minimal current in the TLC5916 special mode is 25%. If you want to be able to dim all the way down to 0%, then you can use the PWM solution for dimming instead, and you can find that hex file and the source code on my website as well. Just click the link in the description.
Now, I really like the TLC5916. I think it's a super useful chip and I'll be using this a lot in the future. But at the beginning of the video, I promised you that I would tell you about my life before I met the TLC5916.
If you have been following this channel for a while, you will notice that some of what we talked about today sounds very familiar. The LED scrolling text display. It's true, in that project we used the CD4094 shift registers to run small 7-segment LED displays. But using the CD4094 was a bad idea for 2 reasons. First, when you look at the schematic back then, you see that we only used 1 current limiting resistor on the displays, but we actually would have needed 1 for each segment. This way, the number 8 with 7 segments turned on is dimmer than say the number 1 which only has 2 illuminated segments. In practice though, you don't really notice it that much with the displays I use, so we kinda got away with it. The second problem is worse. If you look at the CD4094 datasheet, you see that at 5 volt operating voltage, each output can only supply a maximum current of 1 milliamps. And that's really not a lot, but it's not surprising because the CD4094 is a shift register and not a driver. Now again, this worked well for our displays back then, but if you want to connect larger displays to the CD4094, you'll realize quickly that it just doesn't work because they're way too dim, which is exactly what happened to me, as you can see in this video right here.
Now, I hope I could show you today that the TLC5916 is the best driver for LEDs on a breadboard, and I will be using this a lot in the future. If you are wondering what the circuit was that I waved into the camera just now, that will be a future project on this channel if you stick around. Thank you so much for watching and I'll see you next time.